and share the slides. Okay, can you see the slide okay?
Yes.
Looks good.
Yeah, it does move forward. Good. So let's get started. The 230B lecture on April 16. So again, as usual, just logistics. So the solution set to the previous homework problem will be posted today. I'm mostly done, and I'm sure I can do that later today. And we'll have discussion section at 5 p.m. today. And as usual, I'd like to ask you if there are any subjects you'd like to see covered. And some of the requests from the previous week is the conformal field theory and the connection to fiber bundle. And there was also a request to talk about topological methods. And I hope we can get started a little bit in the lecture today. But I'd like to see if there's any further interest in this. So if you have some particular subjects you want to see discussed in discussion section, do let me know. You can send me emails and whatever. Okay. So we'd like to wrap up discussion on dynamics and non-abelian gauge theories. And as I kept emphasizing here, so non-abelian gauge theory becomes strongly coupled at long distances in infrared. So to some extent, all we know is based on some educated guess. But nonetheless, there is some picture emerging what the non-abelian gauge theories are actually doing in the long distance limit. So that's what I'd like to talk about today. So suppose you have the SUNC gauge theories. And so the quarks, psi, is a Dirac fermion that comes in the NC plet. Number of colors is NC here, an NC plet of SUNC gauge group. And you can also talk about other possible gauge groups too. And I briefly mentioned how things are different in the cases later. But let us just focus on SUNC gauge theories for now. And in particular, we'd like to talk about the massless limit of these matter fields, psi. So M of the matter field, I assume, is 0 for the purpose of discussion right now. And the reason is that if you actually take that limit, sorry, I made a mistake here. If you take that limit, this actually limit is fairly close to what we think is happening in the real world QCD, the theory of strong interaction. And also that if this mass is too large, very large compared to the energy scale where the theory becomes strongly coupled, then you can integrate those heavy particles out first. And at the end of the day, you will be actually looking at theory with only light particles. So without loss of generality, talking about the massless limit is a good thing to study anyway. So whether you really do have light quarks, or even if you do have heavy quarks, you can integrate them out before you actually start talking about dynamics of theories at scale lambda, where coupling becomes large. So either way, considering the massless limit is a good one. So that's why we consider the massless quark limit. And once you actually turn off this mass term, what would happen is that this kinetic term for the fermion field would then decouple into two pieces. And the one piece that has to do with the left-handed chirality fermion, namely this psi left, has the eigenvalue of gamma 5 to be -1. And the piece that has the right-handed chirality fermion, namely that the eigenvalue of gamma 5 acting on psi r is +1. And there's no communication between the two. So psi left and psi right then starts acting like a totally different fields on their own. And if you imagine that you have NF, this is the number of flavors, NF number of Dirac fermions in this theory, then the psi left comes with this NF species going from 1 to NF in a column vector. And this kinetic energy term of the Lagrangian is invariant under an arbitrary UNF by UNF unitary rotation, which is denoted by U sub L in this on this slide. And you can do the same thing for the right-handed fermions. Again, the right-handed fermions come from 1 to NF species, so there are NF flavors of them. And I can freely rotate this column vector by another NF by NF unitary matrix U sub R. And I don't need to take U sub L and U sub R to be the same. They are independent matrices. And this is the global symmetry. So U left, U right are constants in space-time. So they are not gauge symmetry, which depends on space-time positions. So you need to rotate the fermion fields the same way everywhere in space-time. But nonetheless, if you do so, then the kinetic term is invariant under this UNF left times UNF right symmetry. And this is what is called the chiral symmetry of the QCD type theories. So the QCD type theories, which have SUNC non-abelian gauge theory coupled to NF Dirac fermions, which we call them quarks. And if quarks come in NF species, then you have this UNF left times UNF right chiral symmetry, so that you can rotate the basis of left-handed fermions and right-handed fermions independently from each other. So this symmetry plays an important role for the discussion on the dynamics of this theory. Okay, so let me stop here. Are there any questions about this symmetry?
So you have SU of NC and then NF and UNF. Are they all supposed to be NF or NC? Or am I confused?
So they act on different space. So in this notation, psi left comes with this NF dimensional column vector. But each entry, so let's say psi 1L, is also NC dimensional column vector. And in addition, psi left is two-component spinor. So what I'm writing symbolically as a column vector for psi left here is actually NF times NC times two-dimensional column vector.
Okay, so NF really is like, so the flavor is like, that's strange up down, that kind of thing is
That's right, that's right, yeah. So in the real world strong interaction theory, then we have three light fermions, up quark, down quark, and strange quark. So psi 1, let's say, is the up quark, psi left is the down quark, psi 3 is a strange quark, and we finish there, so NF is 3. And then you have U3 cross U3 chiral symmetry.
I see. So it's a unitary transformation among the different, actually among the different flavors of the right-handed flavors or whatever.
That's right, right.
Okay, I see.
So NF is 3 in the real world QCD, where quarks can be regarded nearly massless, not exactly massless, nearly massless. So taking massless limit is a good approximation to get started with. And each three flavors of quarks come with three colors coupled to SU3 gauge theory. And each psi is four-component Dirac spinor. So if you decompose that to left-handed, right-handed components, the left-handed chirality components have two components, and so do the right-handed ones. So this psi left vector is actually 3 times 3 times 2-dimensional column vector. And so is psi right. Okay, so thanks for asking the question, Max. Any other questions here?
Yeah, I have a question on the notation in the Lagrangian.
Okay.
So you have like psi left bar and psi right bar. Should those be psi left dagger and psi right dagger? Because
okay, because?
Yeah, because it seems like basically the left and the right have been uncoupled and they're really just two component spinners now. So
yeah, so that's a good question. So if you remember from QED, psi bar is psi dagger times gamma naught, right? So if you write gamma naught times gamma mu as a matrix sometimes called sigma mu or sigma mu bar, then the matrix can be just 2 by 2 matrix. Then this psi bar can be written as just psi dagger, and you're completely right about it. But right now, I'm still keeping this gamma mu matrix, and gamma mu anti-commutes with gamma 5. So if I act gamma mu on psi left, then gamma mu psi left is actually right-handed. So I have to compensate that right-handedness to go back to left-handed fermion, and that's why I need to insert gamma naught in addition to taking Hermitian conjugate. So I still need to write this psi bar to indicate the gamma naught is supposed to be still there. Okay, go ahead, Nick.
Yeah, sorry, I guess I'm just a little confused. So the psi left is now a 2-component spinner, right?
No, I'm still using
I mean,
notation
it's
that I'm still using 4-component notation, just that the remaining 2 components are meant to be just 0. So let me try to write it
okay,
here.
okay. I follow. I see what you're saying.
Okay. Let's see. So psi, oops. Sometimes my iPad forgets about Apple Pencil. Does this work? Okay. So psi has 2 components of psi L and 2 components of psi R. And gamma mu is often written this way. And sigma mu is a 2x2 matrix. And so are sigma mu bar. And gamma 5 is -1, 1. So when I write psi left bar, I gamma mu d mu psi left. What I mean by this is that I first take this psi left dagger, but I set the right-hand components 0 for now. And then I have this gamma mu. And I forgot to write the gamma naught, which was crucial for this discussion here. And then psi bar, has, in addition to this Hermitian conjugation, I need to stick in gamma naught, which is 1, 1. And then comes gamma mu, sigma mu bar. And then d mu psi left. Then I can write this purely in terms of 2-component notation, like this. So this is what Nick was asking about. So you can certainly write everything in terms of 2 components only, then this is only dagger instead of bar. But in order to recover this 2-component expression, I had to stick in gamma naught in here. And that's why I retain this notation with bar in it, because I'm still writing this gamma mu here. So I could have written it either way. But when I said that the kinetic term decouples into 2 pieces of left only and right only, I was still using this 4-component notation where psi left had these right-hand components vanishing. In the same way, when I talked of psi right, I have these 2 components vanishing. And so that was a notation I was using on the slide.
Yeah, that makes a lot of sense. Yeah, I was used to seeing like a massless Weil equation. You would just see the 2-component notation. But that makes sense.
Okay, good. Good. Thanks for asking that question. So let me stop sharing the whiteboard. Go back to the slides. Okay. Any further questions on this slide? All right. And what is believed to happen in this theory, and again, I'll emphasize this again, that the theory becomes strongly coupled, so we don't quite know exactly what happens in the perturbation theory, but based on the experience with the real-world QCD and various other circumstantial evidences based on numerical simulations and so on and so forth, this is what we believe would happen in this theory. So we just talked about the fact that this theory has this U and F cross U and F chiral symmetry. And if this symmetry were exact, it doesn't allow for the mass of the fermion. So the taking massless limit gives us this symmetry. So this symmetry actually doesn't allow the mass of the fermion. So if you would like to write a mass term for the fermion, then you have to combine psi left bar with psi right and psi bar right with psi left to write the fermion mass term. So UNF cross UNF symmetry is no longer a symmetry anymore. So this chiral symmetry is a symmetry that is there strictly in the massless limit. So that's the limit we are considering right now. And under this symmetry, what is believed is that you write this the fermion bilinear psi left, psi right bar, and this fermion bilinear would transform under this UNF cross UNF symmetry by acting U left from the left-hand side, U right dagger from the right-hand side, because that's the way the psi left and psi right transform. So this psi left, psi right bar is a Lorentz invariant. It's a scalar object, but it's not invariant under this UNF cross UNF symmetry. So this is actually a NF, the representation of UNF times UNF. And what is believed to happen in this theory, when the theory becomes strongly coupled, is that this fermion bilinear psi left, psi right bar actually acquires an expectation value. And this is sort of similar to what happens in, let's say, superconductivity, where you have a fermion bilinear to acquire an expectation value. So in that case of superconductivity, you have electrons in system, and two electrons sort of get bound together very loosely in Cooper pairs, and the pair of the electrons acquire an expectation value. And that actually leads to something very close to the Higgs mechanism, and we'll come back and talk about this in the later chapters. So in a similar way, here we are talking about fermion bilinear. So psi left is a fermion, psi right bar is also a fermion. So this is a fermion bilinear, and two fermions together become a Lorentz invariant combination and acquires an expectation value. And when this fermion bilinear acquires an expectation value, because this fermion bilinear transforms as UL from the left, U right dagger from the right, then this expectation value actually spontaneously breaks this UNF cross UNF symmetry. And the only thing that remains is to take U left and U right, the same matrices. And if U left and U right are the same matrices, then this expectation value, which is proportional to the identity matrix, would remain invariant. So what we say is that UNF vector symmetry is unbroken. And the notation of what's meant by vector is to take left and right to be the same. So this is vector instead of axial vector. So axial vector would be parity odd. And that's why, so that refers to U left and U right to be taken actually the opposite. So that would be U axial. But U vector is the parity even component. So you take U left and U right to be the same matrices. So this UNF vector symmetry is still unbroken with this expectation value of fermion bilinear, but the original symmetry of UNF left cross UNF right symmetry is no longer the symmetry of the ground state. And once this symmetry breaking occurs, because left and right now have to transform the same way, all of a sudden, the mass of the fermion becomes allowed. And this is how we believe that the mass of the proton is actually generated in the theory of strong interaction. So again, as an approximation, we can take up quark, down quark, strange quark masses to be zero as a zeroth order approximation to the theory. So in that theory, we have U3 left cross U3 right symmetry. So the way it stands, we are not allowed to introduce any mass for the fermions under that symmetry. But because the ground state now spontaneously breaks U3 cross U3 symmetry to U3 vector symmetry, where I can only rotate the left-handed fermions and right-handed fermions the same way now to be consistent with expectation value, then all of a sudden, I will be allowed to introduce mass for fermions because left and right now rotate the same way. And this is how the mass of the proton becomes allowed. And because this expectation value of the fermion bilinear is believed to be the consequence of the coupling constant becomes very strong, then the size of this condensate should be of the order of the strong scale lambda, where the coupling constant diverges. And as a result, mass of the proton is generated only according to the symmetry breaking that happens at this energy scale lambda. And that's how we believe the mass of the proton is generated. So I did mention this a couple of times already by now, but the mass of the proton is believed to be the consequence of the coupling constant blowing up and going infinite, and that actually in turn creates this spontaneous symmetry breaking. And that spontaneous symmetry breaking then in turn allows for the mass of the proton to be generated, and hence mass of the proton is a consequence of the strong dynamics of this non-abelian gauge theory. So that's the idea, that when you actually take this non-abelian gauge theory in general, SUNF gauge theory, you have this chiral symmetry of UNF left cross UNF right. And then we expect this fermion bilinear to acquire an expectation value, so that symmetry gets spontaneously broken to UNF vector. And as a result of the spontaneous symmetry breaking, we believe that baryons actually become massive as a result. So I mentioned this already. So when you actually weigh your weight or measure your weight on a scale, then you're mostly measuring the mass of the protons and neutrons in your body. And that is actually a consequence of the spontaneously broken chiral symmetry, which allows for the mass of the proton and neutron to be generated, even though the mass of the up and down quarks are so small that this chiral symmetry is actually a very good symmetry of the non-abelian gauge theory, in this case QCD. Okay, any questions about this? Is it okay? All right, so if this picture is correct, then immediately you have a prediction, right? Because once you have spontaneous symmetry breaking of a global symmetry, then you need to have the number Goldstone bosons. And UNF left has a symmetry with NF squared generators. UNF right also has NF squared generators. Unbroken symmetry is UNF vector, which also has NF squared generators. So I have NF squared plus NF squared minus NF squared, broken generators. And therefore, you would expect NF squared number Goldstone bosons. So again, going back to the real world QCD, let's check if that makes sense at all. So here again are the mass of the three quarks, up and down and strange, and they are all very light. And the mass is small compared to the strong scale lambda, which is of the order of 300 MeV. So you can ignore these quark masses at the beginning as the starting point of the discussion, and hence you have U3 cross U3 chiral symmetry. And what we just talked about is this possibility that this chiral symmetry gets spontaneously broken to a diagonal subgroup, namely this U3 vector. And as I mentioned just a minute ago, then you would expect NF squared number Goldstone bosons, which transforms under the adjoint representation of this unbroken UNF vector symmetry. So in the case of the QCD, you would expect 3 squared, namely 9 number Goldstone bosons. And because the broken generator will correspond to taking U left and U right to be opposite from each other, and therefore the generator would be parity odd. Unbroken symmetry is parity even. The broken symmetry is parity odd. So correspondingly, you would expect the number Goldstone bosons to be parity odd states. So what you're looking for is the number Goldstone boson. They have to be spin 0. And also the parity even. So such particles are called pseudoscalars. So scalars, as you know from the Klein-Gordon theory, is meant to be Lorentz invariant spinless particles. But when you say pseudoscalar, you are specifically talking about parity odd scalar particles. And then you can look for the data and see if they are indeed the pseudoscalar particles that form a 9-plet or nonet under SUNF vector as an adjoint representation. And in practice, this U3 cross U3 symmetry is not exact because we know that quarks actually have small but finite masses. So you can actually start doing a perturbation theory with the small quark masses. And then you find that these pseudoscalar states received a finite mass because they are no longer exact number Goldstone bosons, then you say they are pseudo number Goldstone bosons. And the word pseudo is now used for two different purposes. For the word pseudoscalar, the pseudo is meant to indicate parity odd state. When you say pseudo number Goldstone bosons, the word pseudo in this case means it's not quite exactly, that's pseudo, so that they are massless particles in the limit where quark masses go to absolutely zero, but their mass is not exactly zero anymore because they are pseudo number Goldstone bosons of the pseudo Chiral symmetry. And then you can work out how the mass of this number Goldstone bosons are generated. And it turns out that the mass squared of these states go proportional to the sum of two masses, which make up this bound states, a number Goldstone boson. So in the case of M pi, let's say pi plus is made of up quark and anti-down quark, then the M pi squared goes with M up plus M down. And on the dimensional grounds, to make up a quantity of the mass dimension 2, you need to have another mass dimension to accompany M up plus M down, which has mass dimension 1. And the only thing there can be is the strong scale lambda. So expectation here is that you are looking for 0 minus pseudoscalar boson whose mass squared is suppressed by the smallness of the quark masses. And indeed, you find such particles. And for the case of pi plus, you're talking about up and down quark. Case of pi naught, you're talking about UU bar and DD bar. And once again, the expectation of M pi squared would be M up plus M down times lambda for pi naught particle. K naught is the bound state of anti-strange quark and down quark. So in that case, you would expect that the mass squared of a K naught will be proportional to M down plus M strange. And you do find such particles in nature, and you can verify this expectation or prediction out of this idea of spontaneous chiral symmetry breaking, namely that mass squared ratio would cancel this fact of lambda in here. So what you would expect is that that would go only as a ratio of the sum of the quark masses. And if you plug in numbers, the sum of the quark masses would have the ratio of about 0.07, looking at this mass table of the quark masses. And you can also look at the mass of these, the pseudoscalar mesons, and they are the bound state of quark and antiquarks, right? And the pi naught has mass 135 MeV, K naught has mass 498 MeV. You take the ratio of the square of the masses, and that comes out to be 0.074. So you can see that this actually works quantitatively. And given that the quark masses have rather large uncertainties, this can be viewed as a successful prediction of this concept of spontaneous chiral symmetry breaking, which would predict that there are these light pseudoscalar states, and you can predict their masses of the light pseudoscalar states, and the predictions would pan out to be consistent with experimental data. So that's how we know that this idea of spontaneous chiral symmetry breaking seems to work in terms of describing the real-world QCD, and we expect this success would be there for all non-abelian gauge theories when you have NF massless flavors. But one thing we also learned from the experimental data is that, well, if there are supposed to be 9 number Goldstone bosons, on this chart here, I indicated 8 of them: K naught, K plus, pi minus, pi naught, pi plus, K minus, K naught bar, and another thing in the middle called eta naught. And this is written on the plane of what is called the isospin, which corresponds to the number of up quarks minus down quarks. And the vertical axis corresponds to negative number of strange quarks. Then they form this rather nice diagram with 8 particle states on it. But we are missing yet another one, which is often called eta prime meson. And eta prime meson, there is actually a particle which is pseudoscalar, with the correct quantum numbers, but it weighs as heavy as 958 GeV. And this is actually heavier even compared to proton and neutron. So it is very difficult to swallow this idea that this particle is a number Goldstone boson. it's not light. So its mass is not suppressed by the small quark masses. So even though you can find this candidate state, which has the correct quantum number to be the 9th non-Goldstone boson, because its mass is so heavy, it's difficult to see how this could be a non-Goldstone boson of any sort. And this is a puzzle, which is called the U1 problem, because what you would have expected is to find 9 number Goldstone bosons, which correspond to spontaneously broken U3 axial symmetry. That's the parity on combination of U left cross U right. And you indeed do see 8 of them consistently with expectation. But there's a missing piece, which corresponds to U1 part, namely overall phase part of UNF symmetry. So UNF is, roughly speaking, U1 times SUNF. SUNF has a unit determinant, doesn't have an overall phase. The overall phase is contained only on U1 part. And what we have expected is that there should be a number Goldstone boson which corresponds to this U1 part of the symmetry. But such a state doesn't seem to exist. Or if it does, it's apparently very heavy, so the symmetry seems to be very badly broken. And we will come back and talk about this later, I hope today, that this U1 problem now we think is understood. And based on this idea that UNF cross UNF symmetry, even though it's a symmetry of the classical Lagrangian, it's actually not a symmetry of the full quantum theory. And classical symmetry of the Lagrangian can be broken due to quantum effects. And then we say the theory is anomalous. So anomaly means that the classical symmetry of the Lagrangian is no longer symmetry of the quantum theory. And this U1 part of the symmetry is anomalous, namely that it's broken by quantum effects, while SUNF part of the symmetry is still unbroken, even including quantum effects. So that's the way we reconcile the absence of the number Goldstone boson for U1 piece with the symmetry of the Lagrangian we have. So the bottom line is that, okay, we write this Lagrangian of a QCD, which has classically U3 left cross U3 right symmetry. And the idea that U3 left cross U3 right symmetry spontaneously broke the U3 vector seems consistent to the extent that we do get these 8 Goldstone bosons. But we believe that U1 part of the symmetry is broken by quantum effects anyway. And therefore, true symmetry of the theory is only SU3 left cross SU3 right, not U3, but SU3. And SU3 symmetry has only 8 generators, and therefore seeing 8 number Goldstone bosons is exactly the right expectation. So that's the way we try to reconcile the absence of the 9th number Goldstone boson with the symmetry of the Lagrangian. And how exactly the symmetry gets broken quantum mechanically is a question of the perturbation anomalies, which is the discussion of I hope, the second half of my lecture today. So that's how we'd like to proceed and discuss it. But at this moment, emphasis here is that this expectation that chiral symmetry gets spontaneously broken by the expectation value of the Fermion bilinear, which is the autoparameter of the symmetry breaking, does seem to work experimentally because we do identify 8 number Goldstone bosons as expected from SU3 left cross SU3 right symmetry spontaneously broken to SU3 vector. And the prediction works even quantitatively because we expect the mass squared of the number Goldstone bosons to be proportional to the sum of the quark masses, and you can verify those predictions. So that's the idea of the chiral symmetry breaking in non-abelian gauge theories. Okay, let me stop, and I'm sure there are questions.
So I think I might just be mixed up about how these masses are related to what we looked at earlier. But we've been looking at the evidence for the linear confining potential as being the mass versus J. Is that how is that? Am I just missing it? Is that just consistent with these masses as well?
So we are looking only at the j equals 0 state now, right? So all of these states are pseudo-scalar. So they all have j equals 0. And with mass squared proportional to j, for j equals 0, mass squared can be 0. And of course, this linear relationship was only approximate, and we justified it with this linear potential binding quark and antiquark together in a semi-classical analysis. So there could be an offset, but the point here is that we are specifically only looking at the j equals 0 state, and expectation of the pseudoscalar states being Goldstone bosons is that these j equals 0 state are supposed to be exactly massless in the limit where quarks are massless.
Okay, makes sense.
Okay, good. Any other questions here? And actually, the reason why these are regarded Goldstone bosons is really that Nambu came up with this idea of spontaneous symmetry breaking specifically for the purpose of understanding why the pions are so much lighter compared to protons and neutrons. So if you just imagine that the pion is a bound state of a quark and an antiquark bound together within the size of something like a 0.7 Fermi, 1 Fermi is the 10 to minus 15 meter, femtometer. And if you just put a massless particle into that finite size cage, it's confined, it's a finite size cage, then you would expect that it has the kinetic energy of the order of h bar c over the size of the bound state. And that's what you expect from the uncertainty principle. And that is of the order of like a 300 MeV. So if you put two particles into this finite size cage, each of them carrying kinetic energy of something like 300 MeV, then you would expect the bound state to have, substantial mass of the order of 600 MeV or nearly even GeV. But the pion mass is much, much smaller than that, 135 MeV. So it was actually a puzzle. How come that such a bound state of quarks inside such a small size can have a very light mass at the end of the day? And the explanation then is that, well, okay, the pion is light because it is supposed to be a Goldstone boson in the limit where quark mass goes to 0. So it is actually finite mass because the quark mass is not exactly 0, but its mass squared is suppressed by the smallness of the up quark and down quark masses. And that's how we now understand how come there is such a light bound state of quark and antiquark, even though the size of the bound state is as small as the femtometer and less. So that's what earned Nambu a Nobel Prize as a discovery of the concept of this spontaneous symmetry breaking relevant to the explanation of the spectrum of the strongly interacting system. Okay, so given that, we talk about more generally about the dynamics of the non-abelian gauge theory. And so the idea that low energy limit of this QCD-like theory based on SUNC, SONC, and SPA2NC gauge theories can be described by the space of the ground states. And the space of ground states, or coset space, can be described in the following way. For SUNC gauge theories, just like we just talked about, you have SUNF left cross SUNF right symmetry in the Lagrangian, and U1 portion, we will come back and talk about this, is actually broken by quantum effects, so we no longer consider that as an exact symmetry. And this SUNF left cross SUNF right symmetry is spontaneously broken to SUNF vector by the fermion bilinear condensate, and therefore the space of ground states, or the coset space, is this SUNF left cross SUNF right over SUNF vector. And so that's the NF squared minus 1 dimensional space. And the ground state can be anywhere on this space. So you do find the low lying degree of freedom, namely the Goldstone bosons, which move along this direction of the possible ground states. And therefore, what you do is introduce this matrix valued field U of X. And then U of X is given by this TA generator, and TA corresponds to the broken generator. So that's an axial SUNF symmetry. And the pi A is the field that describes this Goldstone degree of freedom. And pi A is a scalar field, so has mass dimension 1 in 4 dimensions. So it needs to be compensated by something parameter of the mass dimension 1, which is called f pi or pion decay constant. And the pion decay constant basically represents at what energy scale the symmetry is broken. So that is a substitute to the size of the symmetry breaking autoparameter. And because of the symmetry, this matrix value field Ux transforms under the SUNC symmetry, like GL U of X, G right inverse. And I switched the notation of the unitary matrices from U to G because I'm now using U to describe a field. I need to use a different symbol to describe the symmetry rotation. So I switched the notation of using G left and G right for SUNF left cos SUNF right symmetry. And U of X is the number-Goldstone boson field. And then you write a Lagrangian that's consistent with the symmetry. And here we go. That's the only Lagrangian you can write consistent with the symmetry and at the leading order in derivatives. So this term has 2 powers in derivatives. And this is the only term you can write consistent with the symmetry requirement. And this is a non-renormalizable theory because you have this dimension 4 coupling constant f pi. And I'm afraid actually this is a typo. So f pi should be upstairs in a coefficient of the kinetic term, which cancels one of f pi coming from the Taylor expansion of u in power series in pi a, so that it has the correct canonically normalized kinetic term for each of the pi a. And in principle, you would write higher derivative terms in the Lagrangian. So this is supposed to be the leading term in the low energy limit. So this is what is called the derivative expansion of the theory, namely that you are expanding theory in power series in derivative, which is the 4 momentum, over f pi, which is a dimensionless ratio. So this is the second power piece in the expansion in p mu over f pi. And you can also have the p mu to the p mu over f pi to the 4th power, p mu to f pi to the 6th power, and so on and so forth. So that is the derivative expansion from the low energy limit. And this is the leading term. And already at the leading term, because exponential has any higher powers in pi a, this Lagrangian already contains interactions among the number-Goldstone bosons pi a. So this Lagrangian in particular would make a prediction on how number-Goldstone bosons will scatter against each other in the low energy limit. And that's something you can also compare to experimental data. How the pions can scatter against each other is something you can measure experimentally. And this whole concept of the chiral Lagrangian, that the number-Goldstone bosons live on this coset space, gives you a definite prediction on what the scattering amplitude should be. And they actually also agree with each other with experimental data. So that's yet another non-trivial confirmation of this whole idea that the non-abelian gauge symmetry would lead to the condensate of fermion bilinear and hence spontaneous chiral symmetry breaking. And if you go to other gauge groups, like if you go to SONC gauge groups, then you can have NF vial fermions, all of them are left-handed. Then you have SUNF left symmetry. Then you find that the fermion bilinear is made of NF Y fermions and times the Y fermion itself to form the bilinear. So that would actually maintain only SONF symmetry unbroken. Then you can find this coset space of SUNF left over SONF. And again, you can write a similar chiral Lagrangian for that. If you have SP2NC theory, you again start with the certain number of Y fermions. And it turns out that there's a constraint because of, again, that has to do with anomaly, we'll come back and talk about later. The number of such Y fermions have to be even for the theory to be consistent. So that's why you have SU2NF symmetry. And again, you expect the fermion bilinear to have a expectation value that would end up breaking the symmetry to SP subgroup of SU2NF. So you again find this kind of coset space, and you find number-Goldstone bosons living on the coset space, and their low energy limit is described by this, what is called the chiral Lagrangian. So this way of writing Chiral-Lagrangian goes back to a paper by Callan, Coleman, West, and Zumino. And Bruno Zumino was a former member of a department. And so that's what we believe what would happen in the infrared or long distance limit of non-abelian gauge theories coupled to multiple fermions. Okay, any questions about this slide?
So can
Go ahead,
that, are the
Max.
f pi,
Hmm?
are the f pi like parameters that have to be fit, or you can compute them from the microscopics?
Yeah, so you can compute it for microscopic physics if you can work out non-perturbative physics. So if you actually put the QCD on the lattice, then you can compute f pi, but not perturbatively. So the only thing we can say from perturbation theory is that if pi is of the order of lambda where coupling constant diverges, that's the best you can say. And you have to resort to techniques like lattice numerical calculation to really work it out quantitatively.
And are the and so this doesn't have the masses of the mesons in it.
That's right. So this is strictly in the massless limit of quarks. And if you put in the mass of the quarks in it, then you have to put in the correction term to it. And the correction term would look like this. So the correction term is coming from the mass of the quark. And let me write it in a particular fashion to be suggestive. So this M is a matrix of, let's say, up, down, strange quark masses. And I'm writing the quark mass term in this matrix notation. And the reason I write it this way is that if you pretend this mass matrix is not a constant, but that's something that transforms this way, and of course it doesn't because it's mass matrix is just a number, but suppose you do pretend that the mass matrix actually transforms this way, then this quark mass term in the QC Lagrangian is invariant because U left goes to U left, psi left, psi bar right go to psi bar right, U right dagger. And if this quark mass matrix goes to U right, M U left dagger, then all of these transformations cancel inside trace, and therefore this Lagrangian would be invariant. So using this idea that mass matrix might transform under this symmetry is actually helpful because when you write this chiral Lagrangian, you can put in a correction which is given by this together with some parameter, so that this combination is invariant if U matrix transforms to, again, I have to switch the notation to G instead of U to avoid the classical notations, and M transforming as G right, M G left dagger, so I have to put dagger here to make it invariant. Then this is the only way you can put in the correction due to the finite mass of quarks into the chiral Lagrangian to be consistent with the symmetry properties. And then what you do is to expand this field U out in a power series in this number Goldstone boson. Then you'll find this Lagrangian then leads to the kinetic term for all of them minus mu cube quark mass I quark mass J to the Goldstone boson squared, something like this. So we know exactly what is the correct way of putting the effect of quark mass into the Lagrangian because of the symmetry properties. And once you do find this prediction that mass squared of these number Goldstone bosons will be proportional to some of the quark masses.
Okay.
Okay. Thanks for the question. This is actually a kind of important point. I didn't make a slide for it, so I appreciate the question. Any other questions here? Okay. then back to slides. Where is it? Oh, this is bizarre. I don't see it now. Oh, that's because I was actually in a full screen mode. Now I should see it. There. Okay. And so this is what we think would happen generically for non-abelian gauge theories coupled to multiple matter fields. So then, do we have the full picture of what happens when theory becomes strongly coupled? So what we talked about is that when you have zero number of flavors, namely that's a pure Mills theory with no matter fields, you expect confinement in a rigorous sense that the Wilson loop would behave as the area law. And if we have only one fermion, so NF is 1, then the symmetry is U1 NF cross U1 NF. But I argued, and I haven't explained yet, that that symmetry actually doesn't exist in quantum theory because of the anomaly. So there is actually no chiral symmetry in this theory, and therefore there's no Navier-Goldstone boson. So in this case, you do have one quark flavor, which can form the bound state, like UU bar bound state for the up quark. But that would be the analog of eta prime meson in the real world QCD, which is heavy because there's no corresponding symmetry to make it massless in the massless quark limit. So then you expect the theory to be gapped. And when you go to two flavors and above, we do have this SUNF left cross SUNF right symmetry, which gets spontaneously broken to SUNF vector. So you expect this NF squared minus 1 Navier-Goldstone bosons. The theory doesn't have a gap anymore in the strict limit of massless quarks. So that's what we expect for a number of flavors 2 and above. And then it still leaves the question, is this true all the way up to higher number of flavors? And what we know is the beta function at the one loop level is proportional to this combination. So if number of flavors is bigger than 16 for 3 colors, or more in general, when this 11/3 times NC is less than 2/3 NF, if we have that many flavors, then theory becomes infrared free because the gauge coupling constant flows to 0 in the long distance infrared limit. So that will be very similar to QED. The beta function is positive. As you go to longer and longer distances, coupling constant becomes smaller and smaller, and there is no sense of strong coupling or confinement. And this is the regime we call the infrared free theory. So if we have large enough number of flavors, we expect the theory to become infrared free. And there's an interesting thing that happens just a notch below this threshold of the theory becomes infrared free. So just below this line, the beta function is still negative. So you expect the theory to become strongly coupled at the long distances in the infrared. But if you take the number of colors and number of flavors to be very large, for instance, you could have a situation where B naught has almost near cancellation between this color contribution and flavor contribution. And assuming that cancellation is not exact, that this is still negative, but something of the order 1 instead of large N. But the two-loop beta function could be order N squared, actually, because it comes with this expression in SUN gauge theory. So generically, when NC and NF are both large, but near the point where they cancel in the one-loop beta function, the two-loop beta function can be as important as one-loop piece, which is actually of the order of N squared over F by 4 pi squared relative to the one-loop piece. So you could have actually cancellation between the two. So here, just for the purpose of plotting it, I plot the beta functions function gauge coupling constant, and I took the B naught, one loop piece to be 1, B1, the two loop piece to be 100. So I'm assuming the NC and NF are of the order of 10 or so. And then you can have the cancellation between the two that gives you an infrared fixed point where beta function vanishes. And with this kind of situation, the infrared fixed point is of the order of coupling constant of something like B1 over B naught over 4 pi squared. That's about 1 in this case. So G squared over 4 pi squared, that's the expansion parameter perturbation theory, is actually quite small. So you verify that there is a non-trivial infrared fixed point within the regime of perturbation theory. So you can trust that this infrared fixed point does exist within the validity of perturbation theory. And this may be sort of reminiscent of the epsilon expansion we did in critical phenomena. And when the space-time dimension is only a notch below 4 dimensions, then we could find the Wilson-Fisher fixed point within the validity of perturbation theory. And of course, that was in some sense a artifact of the epsilon expansion, but nonetheless, that picture persisted even when you went all the way down to 3 dimensions, which we could verify using the large N limit. So in the same way, here what we are verifying is that there is an infrared fixed point if you're only notch below this threshold line for the infrared free theory. But we would expect that this existence of infrared fixed point is not just for this epsilon below the threshold, but it would persist over the finite interval below this infrared free threshold. So we expect that there should be infrared fixed point for a finite range of large number of flavors below this threshold line. So this fixed point is called Banks-Zaks fixed point, according to the paper by Banks and Zaks. And so they pointed out that there is this believable infrared fixed point if you're only notch below this threshold line. But we do think now that this behavior of the infrared fixed point persists all the way down to the finite values of NF below this threshold line. So the picture would then be qualitatively different. So for relatively low number of flavors, you expect the theory becomes confined, and then you have a theory of Namu-Goldstone bosons as the bound states in this theory. But on the other hand, if you have a relatively large number of flavors, you expect the theory to flow into the infrared fixed point. Theory becomes a conformal field theory at long distances. And you still have the quark and gluon degrees of freedom in this infrared fixed point theory rather than their bound states. So approaching this non-abelian gauge theory from small number of flavors and large number of flavors then have a clash in between, because they give you totally different kind of pictures on what would happen in the long distance limit. So the question is what happens in between, and we don't know yet. We expect some kind of exotic dynamics. We may have chiral symmetry breaking without confinement. Or we may have confinement without chiral symmetry breaking. We don't know what is happening in between. And this is still one of the unresolved problems in non-abelian gauge theories. So we do have pretty good picture now, starting from 0 flavors, 1 flavor, 2 flavors, and slightly larger number of flavors. We also have pretty good picture on what happens when the number of flavors is large, below this threshold line for the theory becoming infrared free. But in between, we don't know. And there are many speculations about it, but I think the fair statement is that we don't know. Any questions about this slide? Does this silence mean that people are totally confused? Somebody should say something.
So if I think about the, I'm trying to think about the plot for beta of G as a function of NF, right? So I guess at 0, the star goes all the way out to infinity. And then are you saying that Or no, I guess it doesn't go out to infinity, but it goes out to whatever I guess the lambda scale, the symmetry breaking scale is.
That's right, right,
Okay.
right.
And then, so is this, I guess what I'm asking is like, are these exotic dynamics a smooth interpolation between a big lambda and a small lambda, or is there a sharp thing?
You know, we don't really know, but I do have a next slide where we think we know what's happening. So that's the case when we actually make this theory supersymmetric. And when you make the theory supersymmetric, you have a superpartner of the gauge boson, which is called gaugino. So this lambda is meant to be gaugino, which is a fermion, wild fermion, in the adjoint representation, because it has to be have the same quantum number as the gauge boson, which is an adjoint representation. And we also have the superpartner of the matter fields, the quark, is in the fundamental representation of SUNC. So the phi squawk, scalar quark, is the superpartner of quark, is also in the fundamental representation. And you also have specific way that they couple to each other. So then this Lagrangian actually has a supersymmetry to interchange fermions and bosons. In this case, we think we know the full picture, which we owe a lot to people like Natis Heiberg and Ken Intuitigator. And so this is the picture. So, it's the same as the non-supersymmetric case where zero flavor case would lead to confinement. So that's good. But when you actually start putting in a finite number of flavors, first we have this weird situation. The theory doesn't have a ground state. And because you have these scalar fields, squawks, phi, it turns out that these scalar fields run off to infinity, and it's what is called the runaway behavior, so there is no stable ground state. Once the number of flavors becomes as large as NC minus 1, then the situation changes. For the number of flavors being equal to NC, you actually have the theory of composite particles, namely mesons, and you have chiral symmetry breaking. If you go to one step above, NC plus 1, you have the confinement that becomes the theory of the bound states, but no chiral symmetry breaking. If you further go to a larger number of flavors, this is really bizarre. What used to be SUNC gauge theory, which is asymptotically free and becomes stronger in infrared, now turns into another gauge theory, which is SUNF minus NC gauge theory with the same number of flavors, which is the infrared free. The beta function is positive. And therefore, infrared limit of this theory is the theory of the free gauge bosons and free quarks. If you further go to a higher number of flavors, then you do see this infrared fixed point behavior, which we think would happen even without supersymmetry, thanks to the argument Banks and Sachs. And if you further go to a larger number of flavors, then the theory does become infra-free, just like in QED. So in this case, we think we know what's going to happen. And the reason why we believe this is true has to go through a lot of discussions and become technical, so I don't go actually through this. You're welcome to consult this review paper by Cyberg and Intuitigator. But nonetheless, so in this case, we think we know. So it does indicate that the possibility of having composites without chiral symmetry breaking is a possibility of this exotic dynamics. This infrared free different gauge theory is called the dual magnetic gauge theory. It's a totally new possibility we didn't think of on the previous slide. Whether that happens or not in non-supersymmetric theory, still not known. The fact that theory can become an infrared fixed point theory and become a conformal field theory at long distances seems to be confirmed when you have supersymmetry. So we think this is also true without supersymmetry, as we just talked about. But once again, what happens in this middle range of the number of flavors is something we don't know. So with supersymmetry, we think we know, and it's very bizarre dynamics, as I mentioned, that the gauge theory gets switched over to a different gauge theory and so on and so forth. But what happens in non-supersymmetric, non-abelian gauge theory is still not known. And it's very difficult to simulate this on the lattice when you have large number of fermions, because when you have large number of fermions, you have to compute the Dirac determinant, But determinant is a horrible thing for numerical calculation because you have terms with alternating signs. And determinant for Dirac fermion would be a huge size matrix where the number of the components of the matrix is the number of lattice sites. So if you're talking about, let's say, 10 lattice sites in each dimension, that's already 10 to the fourth times 10 to the fourth matrix. So it's a huge matrix with the alternating signs, and determinants are very numerically unstable. So we don't have a good handle on how to simulate the theory on the lattice either. So right now, it's anybody's guess. So that's an open question. And in addition to this mass gap problem in Mills theory, which we think we understand, but it's not proven, so there's still a lot to be understood about the dynamics of non-abelian gauge theory. So the QCD with 3 flavors, we think we understand it fairly well now, but more generally about non-abelian gauge theory with arbitrary number of flavors, we don't have a full picture of it. Okay, any questions about that? All right, so this, I'm sure, is kind of confusing because I talked about all kinds of new concepts all at once, but you're welcome to ask more questions at the discussion section later today. So this discussion finishes up the discussion on non-abelian gauge theories, and then I move into the chapter on perturbation theory anomalies. In Peskin-Schroeder, there's another chapter in between on the operator product expansion, and that chapter is almost exclusively about the nature of the phenomenology of the QCD strong interaction. So I actually leave that to the course on a standard model instead. And because this is a course in QFD, I'd rather stick to the more general ideas in QFD rather than specifically on the QCD dynamics. So I move into this section of perturbation theory anomalies. So we talked about this already. So suppose you have a symmetry of the Lagrangian, then we expect that symmetry would lead to conservation law. That's a Noether's theorem. And we used this fact many times in the discussion of the quantum field theory. But the idea of the anomaly, as I alluded to already earlier, that in some cases, a symmetry of the classical Lagrangian can be lost in quantum theory. And it sounds really bizarre, but it actually turns out that we have seen this before. And dimensional transmutation is already an example of this. So if you look at the Lagrangian Perturbation theory, the only parameter in the theory is G, which is dimensionless. And so the Perturbation theory is classically scale invariant. So correspondingly, you can define a Noether current for it. So this is a definition of the energy momentum tensor in this Perturbation theory. And using energy momentum tensor, I can write this current J mu, which is T mu nu, X nu, the index nu is contracted. And when you actually compute the divergence of this current, then you just take the divergence of this J mu by definition. When the derivative acts on T mu nu, that vanishes because of the energy momentum tensor is conserved. That corresponds to the conservation of momentum and energy. And that, of course, is still true, even in quantum theory, energy and momentum are conserved. So the mu acting on T mu nu is 0. On the other hand, when the derivative acts on X nu, then that gives me G mu nu. So end result is a trace of the energy momentum tensor. And if you take a trace of the energy momentum tensor in this expression, the G mu nu is 4. And I actually have a mistake here. There's a factor of 4 here. So this trace in that term actually cancel against each other exactly. So the trace of energy momentum tensor is actually 0. So that's how you can confirm that there is a conservation law due to the scale invariance of the theory in the Perturbation theory. But what we know, we talked about this already, from lattice calculation, we know that there is a finite mass gap. And that's what we said is a dimensional transmutation, namely classically scale invariant theory ends up developing a finite mass gap, and therefore theory is no longer scale invariant in the quantum theory. And we understood how that works based on the idea in perturbation theory. The coupling constant actually depends on scale. And it blows up at some energy scale lambda. And so the presence of this energy scale lambda is definitely not scale invariant, and therefore scale invariance is lost by quantum effects in this theory. So this is already an example of an anomaly. And so as a result, this trace of energy momentum tensor, which is whether the current of the scale invariance is conserved or not, is actually no longer zero. And if you go ahead and compute this, it turns out that this trace of energy momentum tensor ends up being proportional to F mu nu with the coefficient given by the beta function. So this fact is called trace anomaly. Trace of energy momentum tensor was supposed to be zero because of the classical scale invariance, but turns out to be non-zero quantum mechanically. And because it's a proportional beta function, there's a one loop effect, and therefore it's a quantum effect. And the presence of this beta function means the coupling constant is no longer scale invariant. It's not a constant, so it's a misnomer to call that a coupling constant now. It runs, so it does depend on scale. So non-vanishing beta function is the sign that theory is no longer scale invariant. And that is indeed how we know that the scale transformation is no longer symmetry of the theory. So we already have seen an example of an anomaly, namely symmetry of a classical Lagrangian may not be a symmetry of the quantum theory, and what used to be the conserved current is no longer conserved due to the loop effects. So what we like to see is yet another example of this kind of anomaly in the case of chiral symmetry, so that we can understand this problem, the U1 problem of the absence of certain Goldstone boson I mentioned earlier. So this is the general idea of what an anomaly is. Any questions about this concept? It's okay?
So back when we were looking at the linear sigma model in lower dimensions, is the absence or if spontaneous symmetry breaking were introduced? I have to think about my questions.
Okay.
I'll ask it at discussion.
Okay, good. Any other question? All right, so this is an example of anomaly already, but then I would like to move into the chiral symmetry. So the reason why I have to talk about it is clear. So we had this problem. So if you think that UNF left equals UNF right is really true symmetry of the QCD theory, then we had the disagreement with data because we don't have the ninth number Goldstone boson. So the way we reconcile this problem is that U1 part of the axial chiral symmetry is actually anomalous. So there is no symmetry which corresponds to U1 axial group, and therefore there is no corresponding number Goldstone boson. So the nature of the chiral symmetry breaking in this theory is not UNF cross UNF, but rather SUNF cross SUNF breaking to SUNF. And therefore, you expect only NF squared minus 1 number Goldstone bosons, and indeed 8 in this case of 3 flavors. And we do see 8 number Goldstone bosons in nature, so that's how we reconcile this problem. So what we need to understand now is how come that U1 axial symmetry is not respected by the quantum theory. So that's something we need to discuss now. And to discuss this, I'm following the book here. So we first go to 1 plus 1 dimensional QED because it's just a lot simpler to understand. So in 1 plus 1 dimensional QED, the gauge theory is U1 gauge theory. And we have this kinetic term for the gauge field. We have the kinetic term for the matter field. And the psi left, psi right has charge E. And I'm taking the massless limit here again so that the left-handed component and right-handed components now decouple in the kinetic terms of this Lagrangian, so that it looks like I can freely rotate the face of the left-handed component and right-handed component independently from each other. Namely that we expect that this Lagrangian has U1 left cross U1 right symmetry. So U1 left is a change of the phase of the left-handed component. U1 right is a change of the phase of the right-handed component. And this is indeed a symmetry of the classical Lagrangian. And therefore, we expect conserved currents for each of them. And for each conserved current, I can define a conserved charge. So if this is divergence-less, I take the time component of the current, that's the current density, integrated over space. That gives me the total number of left-handed fermions. In the same way that this gives me the total number of right-handed fermions. And we expect each of them to be individually conserved. So that is the expectation from the classical symmetry of the Lagrangian. Any questions about this? Okay, so the one-dimensional at 1 plus 1-dimensional QED is expected to have these two conservation laws. And we often take two linear combinations of them. If you add left-handed and right-handed together, that gives me psi bar gamma mu psi, and that is the vector current. And this vector current is what couples to electromagnetism. So certainly this vector current has to be conserved. On the other hand, the other opposite linear combination of them, which is the psi bar gamma gamma 5 psi, which is called axial current. And axial current is often denoted as J mu 5 because there's a gamma 5 in it. And it turns out that this axial current is not conserved in the quantum theory. So we believe that there should be two independent conserved currents. I just took the linear combination of them. So classical theory says that J mu and J mu 5 must both be conserved, but it turns out that J mu 5 isn't, and that's the issue of anomaly. So in order to understand this, what we first do is put this theory on a circle. And so here, this is my notation, a convention on gamma matrices. I realized that I made also typo in the homework problems. I'm going to actually correct them later. And so then the Hamiltonian for the Dirac field is actually given by this. And so it's interesting that in 2 dimensions, gamma naught times gamma 1 can be written as gamma 5. So Hamiltonian turns out to be proportional to gamma 5. So we can work out the energy spectrum. So as I said, to make the analysis tractable, I put the space on a loop or one-dimensional circle. And I also put the antiperiodic boundary condition for the fermion field. And the reason antiperiodic boundary condition is better than periodic boundary condition for a purpose becomes clear later. So let's just accept this for now. And with this antiperiodic boundary condition, I can expand this fermion field in the Fourier series, where Fourier wave vector, namely the momentum, is pi times 2n plus 1 over L. So if x goes all the way from 0 to L, then 2n pi, of course, does give me a phase, but 1 times pi gives me the minus sign, and hence this satisfies the antiperiodic boundary condition. And I can take the Coulomb gauge in 1 dimension. So Coulomb gauge is the divergence of A vanishes. And because there's only one spatial dimension, that the x derivative of x component of vector potential vanishes, which means that the vector potential doesn't depend on x. Therefore, vector potential is just a function of time, not on space. So that really simplifies the analysis. So as a result, we can work out the energy eigenvalue of the Dirac fermion, and that's given by this expression. So this 2n plus 1 times pi over L is what is the momentum of this fermion mode, plus E times A, that comes from this coupling to the vector potential. And A, as I said, is a space-time constant, depends only on time. So if you actually have the case when the vector potential purely vanishes, then you have different kind of energy levels for right-handed and left-handed fermions. For right-handed fermion, then sigma 3, looking at the lower component here, so sigma 3 is negative. Negative sigma 3 is positive. So energy eigenvalue goes together with this momentum, like this. And as we learned the last semester, you're supposed to occupy negative energy states, and you're supposed to keep the positive energy states vacant. And here you see why we had to take the anti-periodic boundary condition. If you had taken periodic boundary condition instead, you have energy levels exactly at 0. Then you have ambiguity whether you are supposed to occupy that state or keep it vacant. And I didn't want to have that ambiguity. So instead, by taking anti-periodic boundary condition, then the levels are clearly separated into positive energy states and negative energy states. So there's no ambiguity about filling negative energy states and keeping the positive energy states vacant. So this would be the right-handed helicity state. So this is a kind of special thing in 1+1 dimension, because whenever you have a particle, if you occupy the state that has a positive momentum, so particle will be moving into the right. So the right-handed helicity state or chiral state is called the right mover. And even when you have a vacancy here, that's the antiparticle, because that's a vacancy of the negative momentum state that has a positive momentum. Therefore, that also goes to the right. Both particle and antiparticle moves right. Therefore, they are both right movers. The left-handed chiral state would correspondingly be left movers. And again, you occupy negative energy states. You keep the positive energy states vacant. So what I would like to do next week then is start with this picture when the vector potential vanishes. I gradually turn on the vector potential and see what would happen to these energy levels. And then you can see quite easily that the axial symmetry is actually broken in this theory. So that's how we like to introduce the idea of chiral anomaly using this 1+1 dimensional QED as an example. And that's also part 2 of your homework problem right now. So you actually go through this yourself. Okay, any questions? Nothing at all? Okay. So I definitely would respond to some of the questions you might have about what we discussed in lecture today in a discussion section later today. If there will be additional time, I can start talking about some other topics which you wanted to see discussed. Okay, see you at 5 o'clock.
Thank you.
Thank you.
Okay.
Thank you.
Thanks.
Bye.